I am Sheikh Rashidul Rahman, Assistant Professor, Department of Electrical and Electronic Engineering, University of Asia Pacific. Today I am going to deliver my third lecture about per unit calculation. So already we have discussed the procedure of per unit calculation, the basic equations of per unit calculation in my past lectures. Already we have solved some mathematical problem regarding this issue. We have also discussed the advantages of per unit calculation. So today, in my last lecture, I will solve another problem. So this is the lecture sheet of per unit calculation. So in this lecture sheet, my first lecture, I have discussed the basic equation of per unit calculation. So the basic equation of per unit calculation is, if we want to convert a quantity unit to a per unit, it means that if we want to represent the quantity in a unitless form, then the equation should be, we have to divide the actual value of the unit by the base or reference value in the same unit. So this is the basic equation of per unit calculation. Next, we have discussed about the second equation, how we can calculate the per unit of any device if a old value of per unit of that particular device has been given with a rating of power rating and voltage rating are also given. And if we want to calculate the per unit reactance of this device for a new power base and new voltage base, then we have to use particular this equation. And the third one is, we have to use this for transformer actually to calculate the base voltage of transformer primary to secondary or secondary to primary. So based on these three equations, already we have solved this particular mathematical problems in our previous class. And now in this present class, we are going to solve another mathematical problem. And this will be the end of our per unit calculation lecture. So this is an example of Stephenson book, Power System Analysis, Chapter 6, example Chapter 6, 6.10 actually. So here, a one-line diagram is given for a particular power system. So for this online diagram, there is a generator, that is the generating unit. This is a step-up transformer, T1. This is the high voltage transmission line connected between the line L to M. It means that point L to M. This is a high voltage transmission line. This is a second transformer. This is the step down transformer T2. And here there are two load actually, two motor are connected at a load, M1 and M2. Here there is a symbol actually are given. So we know if these are the three-phase devices, then that should be either delta connected or Y connected. So this is a three-phase synchronous generator, and this generator is Y connected generator, and neutral is grounded through a reactance. This is a transformer, and this transformer primary side is delta connected and secondary side is Y connected, solidly grounded. This transformer 2, the primary side is solidly grounded, Y connected, and secondary side is delta connected. The first motor M1 is Y connected and grounded through a reactance, and second motor M2 is just Y connected, ground is open. So this is the connection type for this particular devices. Now for this online diagram, the rating of all devices are listed here, and for this particular power and voltage rating, their per unit reactances are also given here. Like the generator rating is 300 MVA, that is the power rating. Voltage rating is 20 kilovolt, And based on this rating, the reactance is 20%. That is, the per unit reactance value is 0.20. So this is the three-phase load, three-phase generator actually. Now, if there is nothing mentioned about the type of the device, like if it is single phase or three phase, by default we will assume all the devices are three-phase devices, because this is our power system where three-phase power is transmitted and the three-phase power is generated actually in the generation unit. So that's why by default we will assume that all of the devices are connected here. They are three-phase devices and their rating are given here. These are the three-phase rating, if nothing mentioned in the right side of the question. So this particular question, there is a given, that is the three-phase value is given here, and for transformer 1 this is also a three-phase value is given. For transformer 2, this is the per phase value is given. It means that the single phase value is given. So this is a three-phase transformer, but here the rating is given in single phase. Three-phase rating is not given in the question. That's why here mentioned that is per phase. So if in the right portion of any device mention per phase or single phase or line to neutral, it means that per phase rating or single phase rating is given for the particular device. For motor and 1 and motor 2, this value is given. There is nothing mentioned in the right side. So these are the all three phase rating. The transmission line length is 64 kilometer. That is the 40-mile length transmission line. Series reactance of the line is 0.5 ohm per kilometer. It means that the reactance of the line is 0.05 ohm per kilometer. So if we multiply 0.5 to 64 kilometer, then we will get the total reactance of the transmission line. The question is, draw the reactance diagram with all reactances marked in per unit. So the question is as same as the previous question, which we have already solved. So we have to draw a reactance diagram, and in this reactance diagram, we have to mark the all reactances in per unit. And this per unit should be the new base. And which is the base? Select the generator rating as base in the generator circuit. So we have to select a new base, and the base is the same as the base is the generator. So we have to select the generator rating as our new base or reference base for the one-line diagram, and this should be in the generator circuit. So our reference base power and base voltage at that point, that is the generator side, that is in the generator point. So we have to calculate the per unit reactance for the generator at first for the same rating, and next we have to move on from transformer T1 to transmission line to T2, and then motor M1 and M2. So we have to move on our calculation from very left side to the rightmost side. So there is one problem actually in this question, that is all the values for the devices are given in three-phase rating, but for transformer T2 the value is given in per phase rating. So we have to convert this value per phase to three-phase rating, because the transmission line is three-phase and all other devices rating are three-phase, but a particular one device's value is given in the single phase. So at first we have to convert this single phase or per phase value to three-phase value. So this is our first attempt or the first procedure to solve this mathematical problem. So whenever we want to convert transformer T2 rating for three-phase rating, at that time the power rating for transformer T2 is given 100 megavolt ampere for single phase. So this is three-phase transformer. So if we multiply this power by 3, then we will get the three-phase rating power value for the transformer. So that's why to convert the single phase to three-phase power rating, we have to just multiply the single phase power rating by 3. So the single phase power rating is 100 MVA. If we multiply it by 3, the result should be 300 megavolt ampere. So this is the three-phase power rating for transformer T2. So simply we can convert this value. Now, for the voltage value, the primary and secondary ratio is given 127 by 13.2 kilovolt. So one side should be primary and another side should be secondary. So which one is primary and which one is secondary? At first we have to identify this. We know transformer T1 secondary portion is connected to the load. So the secondary portion of transformer T2 should be the low voltage portion. Now here in the transformer T2 rating, 13.2 is given. So this is the rating of low voltage portion because 127 is much more than the 13.2. So 13.2 should be the secondary portion rating. And 127 kilovolt, this is the primary side rating or the high voltage portion rating. Now, whenever we convert this value from per phase to three phase, we know there is a difference from line to line to line to neutral value. The conversion process is we have to multiply line to neutral value by √3 to get the line to line value. Another way, if we have the line to line value, then to convert line to line value to line to neutral value, we have to divide it by √3. So this is a factor, that is the √3 factor. We have to consider this factor to convert the single phase to three phase. So whenever we convert the single phase or line to neutral value to line value, we have to multiply line to neutral value by √3 to get the line to line value. So here there are two rating are given, one is primary and another one is secondary. So the next question is, should we multiply √3 for both two sides to get the line to line value? The answer is we have to see the connection type at first. So for this reason, we have to see the primary and secondary side connection type for transformer T2. The primary side connection is Y and the secondary side connection is delta. Now we know for delta connection, line to line voltage and line to neutral voltage is same. There is no difference between line to line voltage and line to neutral voltage. So that's why for the secondary portion, the value is given 13.2 kV. This is the delta connection. So this value should be unchanged for single phase or for line to line value. So that's why we don't need to multiply by √3 with 13.2 kV because this is the delta connection, and for delta connection, line to line voltage and line to neutral voltage is same. Line to neutral voltage are same, so we don't need to multiply anything with the secondary portion value of transformer T2. Now for the primary portion or for the primary case, this is the Y connected. So we know for Y connected transformer actually there should be a different for line to line voltage and line to neutral value of voltage, and the difference is if we want to get the line to line value, we have to multiply √3 with the line to neutral value. So for the primary portion of transformer T2, the value is given per phase value 127 kilovolt. We have to multiply with this value by √3 to get the line to line value or to get the three phase rating value. So here we have to multiply √3, and if we multiply √3 with 127, the answer should be 220 kilovolt. And the secondary portion voltage remaining unchanged because this is the delta connection. So now the three phase rating for the transformer T2 is, the power rating is 300 megavolt ampere and the voltage rating is 220 kilovolt by 13.2 kilovolt. So for this transmission line, now all values or all rating are now converted from for three phase actually. So after this conversion, the calculation procedure is same as we discussed in our last lecture. This is the same process. If we consider for the generator, the old power rating is 300 MVA and new power rating is also 300 MVA. So that should be eliminated. The old voltage rating is 20 kilovolt and new voltage rating is also 20 kilovolt. So that should be eliminated. So the reactance 20%, it means that 0.20 per unit. That is our new reactance also. So for generator, the new reactance is 0.20 per unit. So we don't need to actually determine this value once again, because we just calculate this, and no need to conversion. The value should be 20%, that is 0.20 for generator. Now for transformer T1, if we consider the primary portion, we can consider for primary or secondary, the result should be same. But if we consider the primary portion, then the power rating old is 350 megavolt ampere. This is the rating. The voltage rating old should be 20 kilovolt. Here the rating is given secondary by primary, because 230 kV at first, then 20 kilovolt. That is a secondary by primary, because the low tension side should be connected with the generator. And for this reason, the low tension voltage is 20 kilovolt. So we have to just alter this arrangement. So we have to alter this arrangement to identify the perfect voltage rating of the transformer primary and secondary portion. So the primary portion voltage rating should be 20 kilovolt, because this is the low tension side which is connected to the generator. So the old voltage is 20 kilovolt, and the new voltage as the generator base, that is also 20 kilovolt. So the voltage rating is eliminated. Only 350 megavolt ampere, that is the old, and the new is 300 MVA. So if we calculate for transformer T1, the new power rating is 300 MVA, that is the base, and the old power rating for transformer T1 is 350 megavolt ampere. 10% reactance, that is 0.1, and the voltage base are same, so that should be 1. So final answer 0.0857 per unit. So this is the reactance of transformer T1. There is a new per unit reactance. Now, if we want to consider the secondary portion of transformer T1, or anyone you want to calculate the new per unit reactance for transformer T1 by considering the secondary portion or the high voltage portion of transformer T1, obviously you can do this and the result should be same. So whenever we want to consider the secondary portion voltage of transformer T1, then the per unit reactance or old reactance for transformer T1 is 10%, that is 0.10. The new power rating is 300 megavolt ampere, and the old power rating is 350. Now the old base voltage for transformer T1 secondary portion is 230 kilovolt, because this rating is the high voltage rating or transformer secondary portion rating. So that's why the old rating for transformer T1 for the secondary portion is 230 kV. Now the new base voltage for secondary portion of the transformer T1, we have to identify this, because our base voltage is 20 kilovolt, which is at the generator point. So whenever these base voltage shifted from primary to secondary of transformer T1, then 20 kV should be converted to a new base value. And to calculate this, we have to use the equation VB2, that is the base voltage of secondary portion of transformer T1, is equal to VB1, that is the base voltage of primary portion of transformer T1, into E2 by E1, that is the rating of secondary portion by rating of primary portion. So VB1 here 20 kilovolt, the rating of secondary portion, that is the 230 kilovolt, divided by the rating of primary portion is 20 kilovolt. So if we calculate this, this is the calculation, that is the 230 . Well, so how we get this 230, or the transmission line base voltage 230? We don't actually show this calculation in the solution. Actually, well, because one reason, if we want to calculate the secondary base voltage of transformer T1, we can calculate it without using calculator. So how we can calculate this? Very simple. So VB1 is 20 kilovolt, So E2 is 20, divide E2 is 230, that is the secondary portion high voltage, and E1 is 20. So 20 into 230 by 20. So 20 should be eliminated, and here the final base voltage should be 230, because E2 here is 230, E1 is 20. So E2 by E1, that is 230 by 20 into VB1, and VB1 is 20. So 20 should be eliminated, and the result should be 230 kilovolt. So the secondary portion new base voltage of transformer T1 is 230 kilovolt. So this is the calculation we can calculate by just see the rating in our question. We don't need to use calculator actually. So that's the reason we just we don't show this calculator in this particular solution. Well, so 230 kV is the new base voltage of the secondary portion of transformer T1. So the old base voltage is 230. So 230 should be eliminated, and the result is 0.1 into 300 by 350. So the result should be same, 0.0857. So if someone want to calculate the new per unit reactance of transformer T1 by considering the secondary portion, he or she can do this, and result should be the same as we consider the primary portion. Result should be the same. Just one thing you have to remember, in which portion of transformer you want to calculate for per unit reactance, you have to consider the base value old for this particular portion and the base value new for this particular portion. If you consider the secondary portion but the base value you consider the primary portion, your result should be wrong. Or if you calculate for transformer reactance per unit considering secondary portion, and your rating you consider at the primary portion, your result should be wrong. So whenever you calculate the per unit reactance for transformer for a particular portion, like for primary or secondary, you should have put the same portion old base and new base. Then your answer should be same, and your answer will be right. So this is another thing, that if we want to calculate the per unit reactance for transformer considering secondary portion or primary portion, the result is same. So per unit reactance does not affected by the shifting of transformer side. This is unchanged whenever we calculate the per unit reactance. So this is the reason why it is unchanged actually, because whenever we calculate the per unit reactance for any portion, we should have considered the old and new rating for this particular portion, and the rating should be changed by changing the primary and secondary. So that's the reason the base is shifted, so that's why the reactance remains unchanged, or per unit reactance should be unaffected by the shifting of the transformer site. Well, so next, this is the high voltage transmission line. So the base voltage of the high voltage transmission line is 230 kilovolt, because whenever this 20 kilovolt is shifted here, is converted to 230 kilovolt. So that's why the base voltage of transmission line is 230 kilovolt. So this is the base voltage, and base power is 300 megavolt ampere. So if we want to calculate the per unit reactance of transmission line, we have to at first determine the base impedance for the transmission line. And the base reactance or impedance of the transmission line is, the equation should be base voltage square divided by base power. That is the kilovolt square divided by megavolt ampere. And kilovolt is 230 square divided by megavolt ampere should be 300 megavolt ampere. So if we want to calculate the transmission line base, so base should be kilovolt square divided by megavolt ampere. So kilovolt is 230 kilovolt, megavolt is 300. So the transmission line base impedance or base reactance is 176.3 ohm. Now the per unit should be old by new. So old is given 0.5 ohm per kilometer. So our transmission line is 64 kilometer long. So the total reactance for the transmission line is 0.5 into 64 kilometer, and we have to divide this value by the base value, that is 176.3 ohm. so that we can finally calculate the per unit reactance of the transmission line by considering this new base voltage and new base power. And the per unit reactance for transmission line is 0.1815 per unit. Now, we have to calculate the per unit reactance for transformer T2. For transformer T2, again, we can calculate the per unit reactance for transformer T2 by considering the primary side, or we can calculate by considering the secondary side. So in this particular solution, actually, we consider the transformer secondary portion to calculate the per unit reactance. We consider the secondary portion. Okay, so if we consider the primary portion, then what should be the formula? So if we consider the primary portion to calculate the per unit reactance, then the new base power for primary portion is 300 MVA. This is the power base for the whole power system circuit of this particular power system actually. So new power is 300 MVA. And old power is the rating of transformer T2, that is 100 MVA per phase, and whenever we convert it for 3 phase, the rating is 300 MVA we have just get. So the rating old is also 300 MVA. The old reactance for T2 is 10%, that is 0.1 per unit. Now the base voltage actually. So if we consider the primary portion, then the old base voltage for the primary portion is 127, that is the per phase value. Whenever we multiply it by √3, the 3 phase or line to line value is 220 kilovolt. So the old rating is 220 kilovolt square, divided by new rating is the new base voltage of this line, and that is the 230 kilovolt. So if we want to consider the primary portion of transformer T2 to calculate the per unit reactance or new reactance, then the equation should be 0.10, that is the per unit reactance of the transformer T2 old value, into MVA new, that is 300, divided by MVA old, that is 300 also, into kilovolt old, that is 220 square, divided by kilovolt new, that is 230 square. Then we will get the result, and the result should be 0.0915 per unit. Same. So if we want to consider the secondary portion to calculate the per unit reactance for transformer T2, then for secondary portion, the power rating new is 300, power rating old is also 300, and transformer reactance should be 10%, that is 0.10. But the voltage base old should have we consider the secondary portion of transformer T2. And the old voltage for secondary portion is 13.2 kilovolts. So 13.2 square divided by, we have to consider the new base for the secondary portion of transformer T2. So whenever we want to consider the new base of transformer T2 secondary portion, at first we have to calculate this. So the equation should be VB2 is equal to VB1, and VB1 is to 30 kV into E2 by E1, and E2 should be 13.2 kilovolt divided by E1 should be 220 kilovolt, because this is the line to line value 220 kilovolt. So if we want to calculate the new base for secondary portion of transformer T2, we will get the new base 13.8 kV. So VB1 to 30 kV, E2 that is 13.2 kV divided by E1 that is 220 kV, and the new base is 13.8 kV. So this new base voltage is the new base for transformer T2, and similarly this is the new base for motor M1 and motor M2 also, because these are connected with the point N or with the secondary portion of transformer T2. So the old base is 13.2 kV. This is the secondary portion old base for transformer T2, and new base also is 13.8 kV. So this is the new base for transformer T2 for the secondary portion. So if we calculate this, we will get the per unit reactance for transformer T2, that is 0.0915 per unit. Now we have to calculate the per unit reactance for motor M1 and motor M2. So for motor M1, the old MVA is 200 and the new MVA is 300. the old reactance is 20%, that is 0.20, and the old kV, that is 13.2 kV, and new kV, that is the 13.8 kV. So the new base for secondary portion of transformer T2, 13.8 kV. So the equation should be for motor, that is 0.2, it means that 20% into MVA new by MVA old into kV old, that is 13.2, divided by kV new, that is 13.8 kV. Similarly, for motor 2, here the MVA new is 300, MVA old is 100, and the kV old is 13.2, kV new is 13.8, motor reactance is 20%. So this is the equation, 0.2 into 300 by 100 into 13.2 by 13.8 square. So this is the answer. So this is the answer for motor M1 and motor M2, and these are the new reactants. Now the one thing we have to leave, that is the reactance diagram. So reactance diagram is very simple. To draw the reactance diagram, at first we want to see the circuit diagram or the one-line diagram actually for this particular power system. And the one-line diagram is at for very left side, the generating unit or generator is connected. After the generator, the transformer T1 is connected. After the transformer T1, this is the high voltage transmission line is connected. After the transmission line, another step down transformer T2 is connected, and the secondary portion is T2. From this side, two parallel load, that is the two parallel motor are connected. So this is our online diagram, and from this online diagram easily we can draw the reactance diagram. This is the generator reactance and this is the generating source. From the generator, the transformer T1 is connected. So this is the transformer T1 reactance. From transformer T1 to T2, there is a high voltage transmission line connected. And this is the value of high voltage transmission line per unit reactance. After that, the transformer T2 is connected. So this is the reactance of T2. And from the portion of secondary of T2, there should be two motor connected parallelly. So here, this is two parallel branch. One is motor 1 and second is motor 2. And this is the motor electromotive or back EMF source, and this is for the second motor. And the neutral of these two motors with the neutral of generator are connected together. So this is our per unit reactance or reactance diagram, per unit reactance diagram. So this is the complete solution of this particular mathematical problem. So if any mathematical question, the value is given in per phase or single phase or line to neutral, we have to convert this at first to three phase value. Another one is we have to calculate our base voltage from which the base voltage is a perfect match from the question to a particular device, like here the perfect match as the generator portion 20 kV. Or if the base voltage is given 10 kilovolt, then there is no match for 10 kilovolt here, then we can consider our calculation from the generator side, or we can start our calculation by considering the motor side, because the base voltage, there is no match from the given rating from our new base voltage. So if this type of case will happen, then we can start our calculation by this process. If the base voltage is perfectly matched with a particular device, then we have to calculate our calculation from this particular device. So this is the full solution of this particular mathematical problem. So this is an example actually. This is a homework. So this is a simple mathematical problem. So I think you will solve this problem as this mark as a HW. So if the motor M1 and M2, so of example 10.10, or it means that the particular mathematical problem which just we have solved, for this particular problem, these two motor M1 and M2 have input of 120 and 60 megawatt. So this is the input power rating of motor M1 and M2, that is 120 and 60 megawatt respectively at 13.2 kV. So voltage is 13.2 kV, and both operate at unity power factor. So the power factor is unity, it means that 100%. Find the voltage at the terminal of the generator. So we have to calculate the terminal voltage of the generator. So whenever we have to calculate the terminal voltage of generator, so this is the solution procedure actually. So all the values here are given in per unit. So we have to convert the power rating of the motor in per unit value. So the motor power rating together, two motors are taken 120 plus 60 megawatt, that is 180 megawatt power. So if we multiply, if we divided this value by the base value, then we know our power base value for the particular online diagram is 300 megavolt ampere. So if we divided this value, then the per unit value of power should be zero point 0.6 per unit. Now, we know P is equal to VI. It means that voltage into current is equal to 0 0.6 per unit. So this is the magnitude. Mod sign, it means that only we have taken the magnitude. So that is the 0 0.6 per unit. So since the base value of the motor is 13 point, base value of the motor is 13.8 kV. This is the new base, and the old base or the rating of the motor is 13.2 kilovolt. So if we divided this value, we will get the per unit value for the motor. Next, whenever we get the per unit value of the voltage at the motor side, then we find the value of V. Then the I should be power divided by voltage, because I is equal to P divided by V. So this is the per unit value of power and this is the per unit value of voltage. So the current should be 0.6273. Angle 0 degree because power factor is 100% here. The angle should be 0. So cos 0 means power factor 1. So we have to convert the power or voltage rating from the real unit to per unit. Because what is the reason? Because all are the reactance of the motor, generator and the transmission line are in per unit. So whenever the reactance are given in per unit, that time we have to convert the power, current or voltage in per unit to calculate our desired value. So after that, the voltage at the generator portion is a simple Kirchhoff's voltage law actually. This is a simple Kirchhoff's voltage law. All the potential rise should be equal to the potential drop. So here 0.9565. So what is the voltage 0.9565? So 0.9565 is together the voltage at the motor terminal. And if we see the particular reactance diagram, these two motors are connected in parallel connection. So in parallel branch, voltage should be same. So here in parallel branch, voltage should be same. So that's the reason this is the motor terminal voltage 0.9565. Now here there are particular three drops, that is one is according to transformer T2, another one is for transmission line, and another one is for transformer T1. So we have to add all these three drops. So we can apply this Ohm's law. So according to Ohm's law, voltage drop is equal to current into impedance or current into reactance. So by applying this is the value 0.6273. This is the value of current, and this should be these three reactance. So this is the drop actually. So this is the drop 0.9826 angle 13.2. So this is the rectangular form. If we convert this rectangular form to polar form, we will get the magnitude and angle. Now this is the terminal voltage of generator. The result in 0.9826 per unit, but we don't know this 0.9826 means how much voltage. How much voltage? This is a small voltage or this is a big value of voltage. So finally, we have to convert our result to real unit. This is our final work. We have to convert our voltage to real unit, and to convert the per unit to real unit, we have to multiply this value with the base or reference value, and our base or reference value is 20 kilovolt. So whenever we multiply this with 20 kilovolt, this is the generator terminal voltage 19.65 kilovolt. Now one thing you should have remembered, that is we multiply by 20 kilovolt. It means that the base value. But the 20 kilovolt is given in our question. That's not the reason that is we multiply by 20 kilovolt. The reason is at the generator circuit, the new base is 20 kV. That's why we multiply 20 kV as we consider our new or reference value. If our base value in our question is given 13.2 kV, then that should be the perfect match from the motor side. And whenever we consider this and calculate from motor to generator, then at the generator end, the voltage base is not is equal to 20, something more or less than 20 kilovolt. So that time, whenever we want to convert the per unit value to real unit value for the generator side, we have to multiply the base value, which is the new base at that time at the generator point. So we have to multiply by this value. So in our particular problem, the new base at the generator side is 20 kilovolts. So we have multiplied this, and finally we will get the 19.65 kilovolts. So this is our result. Now this particular math is showing the application of per unit calculation, because whenever we want to calculate the terminal voltage of generator, we have to convert the all values of the given power, current or voltage to per unit value. After that, we have to calculate the per unit terminal voltage, then we have to calculate it to real unit, because this circuit, the reactance are given in per unit. So whenever particular complex circuit or for a particular one-line diagram, some values are given in per unit, you have to convert the per unit value to real unit value, or you have to convert the others value, it means that other real value, to per unit value to solve the mathematical problem. After the solving the problem, you can just convert from per unit to real unit value to understand the real impact of the result actually. So this is all of the per unit lecture, and by completing these 3 lectures, just I hope that now you are able to calculate the per unit calculation for any particular power system or any other power system. Now you are able to calculate the per unit calculation. So that's all for per unit lecture. So next class we will meet in a new topic, and that topic should be how we calculate the bus admittance matrix for any power system. So we know that our power system is interconnected. So how we calculate the bus admittance matrix for interconnected power system? So before calculate the bus admittance matrix, we have to know what is the bus admittance matrix actually, or what is the interconnected power system actually. So all these things we will discuss inshallah in our next lecture. So today this is all. So thank you and Allah Hafiz.